Thank you for joining me in the talk about AI in a minefield, learning from poison data. I'm Itsik Mantin, lead scientist at Imperva. In the last 21 years, I've been innovating on security algorithms and their intersection. I love math, I love algorithms, I love the game of understanding threats and designing mitigations. And you can see a couple of pictures of what I do in my spare time. I will start with speaking about AI and the AI threat landscape. I will then zoom into the threat of data poisoning, about when, why, and how this threat is applicable and what can we do about it. I will then speak about how the data poisoning threat is realized or potentially be realized when building a web profile for the sake of web security. And we'll end with summary and conclusions. No doubt, we are in the AI era. Artificial intelligence systems are everywhere and are changing the way people do almost everything. And the AI era is, in fact, also the data era, because data is the fuel that makes all these AI systems work. And AI and data have huge contribution to many domains. However, this contribution comes also with several caveats, which we tend to ignore, or at least to underestimate. And we'll speak about some of these caveats in this session. Most of you are probably familiar with the Gartner hype cycle for new technologies. So equivalent to this, you can think of a security life cycle for new technologies. New technology begins with very little thinking about security, or maybe no thinking about security. People are focused on the technical obstacles and are excited with the applications and the opportunities. At some point, someone discovers that this technology behaves very odd when certain input is being fed to it, and then you have another vulnerability and another one when the technology meets reality. And it sometimes reaches a situation where people ask themselves whether this technology will ever be usable in a safe manner. But at some point, security researchers and domain experts start to work together on building methodology, on modeling attacks and modeling mitigation techniques, and then we get to a stage of a healthy development of the technology in a safe manner, and it reaches at some point a plateau where all the major threats are already being understood, and the threats and how to mitigate them. And still, new threats are being discovered all the time and new mitigations, but the situation is essentially stable. So we've seen this for web in the 80s, for mobile in the 90s, and now we are seeing this for AI as well. I think in the last couple of years, we're starting to see really the discussion about AI threat landscape more seriously than before. What you see here is a typical machine learning system. There is the training part, where training data is being fed into an algorithm that builds a model. This model can be a classification model, it can be a regression model, it can be many other things. And then this model is used to classify or to predict or to process inputs data. This is called inference. And the result is a prediction or classification. In some cases, in some systems, the result of the model is being fed back is being evaluated in order to continue and improve the algorithm or to make it work for a dynamic environment, for example. Now, when you're looking at the system from an attacker perspective, then if the attacker is inside, or if the attacker was outside but somehow found his way in by malware infection, phishing, whatever, then he can do whatever he likes. The sky's the limit. He can tamper with the model, he can steal the model, he can change every particular decision the model makes, he can replace the model with his own, he can, of course, steal the data. However, even if the attacker does not have a foothold inside and is an outsider, then still there are plenty of things this attacker can still do. Some of them are called evasion or deception or adversarial examples. Most of you probably heard or saw this very concerning examples of how you add a couple of stickers to a traffic sign, to a stop sign, And then the AI engine that within the autonomous vehicle looks at this stop sign and identifies it as a speed limit sign. Very concerning, of course, can have devastating consequences. And from I think all the times where someone tried to make to thwart machine learning model, usually it was not very hard. It was pretty easy to do that because machine learning models, when you build something without thinking of an attacker, and the attacker comes, then probably you won't be safe. We know that from many domains, and AI is not different than that. Training data poisoning, we'll speak in depth about this threat later. Training data leakage is slightly more esoteric threat, but still an important one. In many cases, when you build a model, data from the training data leaks into the model, and this data can sometimes be extracted later on. And whenever you use sensitive data for the training, and usually you use sensitive data for the training, it can be either PII or health records, depending on what exactly the model that you're building, but it will probably be sensitive, and then the threat is real and important to understand and to evaluate and to mitigate. And so how does data poisoning work? On the left side, you can see a linear classifier that is aiming to separate between the red triangles and the blue dots. Now, if you only change the location of a single point, then you get a completely different classifier. It is still effective, but it is different, and really, it is very hard to predict or to restrict the change in the model construction due to the change in a small number of data points. And on the right side, you see even a more a deliberate attempt to thwart the model construction. Again, the model here comes to separate between the blue and the red, and the attacker now puts red dots in places that it is clear it will make the model very different than what it was before. And as you can see, the new model now does a pretty lousy job separating the blue from the red, exactly what the attacker wanted to achieve. This data poisoning methodology, terminology discussion is pretty new. I only met it in the last couple of years. However, the threat itself is not new. It is almost as old as the internet. I think at any time, like myself, when you are looking at the TripAdvisor hotel review, then you're asking yourself, is it a real review? Is it a fake review? Is it the hotel owner now that he's trying to convince me that this hotel is very good, although it is not, or it's a competitor? And the same thing, that TripAdvisor also have the same concern. So the threat of data poisoning is there, and people treat it and treat it. And it is there whenever you have a rating system. It can be e-commerce like Amazon, or it can be travel like Booking or Google or TripAdvisor. It can be even movies like Netflix or IMDb. Whenever you have a rating system and the decision of this rating system is meaningful for someone, then probably someone has motivation to make this system making correct decisions. And then you have the data poisoning threat, and usually people understand that and treat it one way or another. One of the first more popular research fields for data poisoning threat and mitigation is the area of spam filters. Maybe one of the reasons is that this is one of the places where machine learning proved itself effective against cybersecurity threats. And on the left side, you're seeing a model skewing attack on Gmail spam filter. The attackers created many messages and classified and labeled them as benign. And these messages had something in common with messages that they probably planned to send later as spam. So you can think of that as sort of a backdoor within the Gmail spam filter, the backdoor that they wanted to inject. On the right side, you see attackers that took, actually this is a research, not actual attack, but a different approach of availability attack. Here, the victim is a spam-based spam filter, and what the attackers try to do is they knew that the algorithm builds a dictionary of spam hints, and they wanted to pollute this dictionary with a collection of probably very popular words that are used in many legitimate emails. And the attack was pretty successful. With only control of 1% of the data used for the training, the researchers were able to make the model classify 80% of the benign email, of legitimate emails, as spam, and 95% of the legitimate emails as unsure. So probably like myself, you see at the beginning, you see this and you say, okay, so the problem is I give the attacker the possibility to do the labeling. So I'll do the labeling and everything will be all right, right? Wrong. Because in this variant of data poisoning, a clean label attack, the attacker does not have any influence about the labeling process. Here, the attacker wants to attack an image classification system. He wants to convince this model that all these fish that you see in the top images are actually dogs. And the way he obtains that, he takes an image of a dog and he adds an invisible noise that is somehow correlated with the images of the fish. He adds these noises to the image of the dog. And now, for us, the image still looks like a dog. For the trusted labeling expert that is working on behalf of the image classification, it also looks still like a dog, and he labels it as a dog. However, the result of this labeling is that the model now will learn that images that have this hidden structure are dogs. And the success of this attack is more than 95% confidence that the model says that the model has when it claims that images of fish are actually dogs. So the threat is there and it's real. How to prevent it? There are two approaches that are, again, they were used even before we called data poisoning. You can filter suspicious data, for example, suspicious origins, IP addresses, or users, or suspicious clients. For example, in Booking.com, I think that you can only provide rating if you did actually a transaction. So it gives some level of reliability to all the actors that give ratings. You can also use a fault tolerant data sampling. For example, limit the impact of data points that are arriving from a single entity. And what is exactly entity? Well, that depends, of course, on the problem itself, on the algorithm, the model, and the situation. So these two are pretty effective, but only to some extent. There are also other mechanisms, mostly for detection, like diff tracking, tracking the difference from the previous model, a valid model, and assume that you have data poisoning whenever you see too high distance, or to use a reliable benchmark, a golden data set that you use all the time to make sure that you don't have a model that is completely corrupted. But again, these two are detection, and their effectiveness is very limited. And of course, you can also assume that the attacker does not know what you are exactly doing, or he knows what you're doing, but he doesn't know the model, and and that the attacker will not know exactly how to attack you, and he will not attack you. But we here in Besides, we know that security by obscurity very rarely proves itself as an effective mitigation technique against any threat. So not recommended. So what we have so far, data poisoning is a significant threat on learning mechanism. The threat is critical when using data from untrusted sources, which is typical in almost every place. It is effective in cyber security domains like firewalls, spam filters, and malware detection, and rating systems like e-commerce or travel. And it doesn't have a silver bullet mitigation. It has a collection of mitigation techniques that together can throttle the attacker. Next, we'll go to the, I'll explain about how this data poisoning threat is realized or can be realized in the world of web and API security. So what you see here is a WAF, a web application firewall between applications and outsider threats, aka the internet. Usually WAFs work using a combination of negative security model and positive security model. I will focus on the later one. So positive security model is essentially the idea that everything is bad except for what we know for sure that is good. So it is sort of anomaly detection. And in order to use that, we need to learn a baseline profile for the web or API traffic and to block or alert on deviation. But when I say that we want to learn a baseline profile, the data that we will use is actually traffic that we've seen through this web API. And if this traffic comes from outside, there you go. We have all the ingredients of a data poisoning attack. So it needs to be treated and mitigated. So web or API traffic profile can essentially look something like what you see here. The red parts here are actually, think of these as carriers of traffic. Can be cookies or query string parameters or body parameters. Each one of them is actually belongs to a host or URL or method or a combination of these, which we call containers. And each one of them has actually a traffic profile. The type of the value that can be for this parameter, whether it can come several times in the same request or only one time, optional or mandatory, parameter size for numeric values, parameter character set and length for strings, and stuff like that. All of these are things that we will want later to enforce because they have some meaning, some significance for detection of web attacks. It makes a lot of sense to use both the mitigation techniques. First, cleaning, filter suspicious traffic. For example, suspicious events, traffic that was identified as malicious by some other mechanism. Maybe traffic from suspicious IPs that are known to generate malicious traffic. Also, maybe sometimes it makes sense to filter all the traffic during an attack, regardless of whether it came, because it makes sense that the possibility of misclassification here is not negligible. Or traffic for bots, it also makes sense in some cases. The next mitigation is threshold learning. Again, limiting the impact of every entity. Entities that make sense can be IP addresses, user agents, geolocations, identified clients. Also, if you want to avoid learning something that came in a burst of traffic, then you want to learn things only when you see them spread along several hours in a day or several days, depending on your exact model. And eventually, once you complete the learning, you can do the enforcement alert on deviations from this profile. Now, the threshold learning here is pretty easy in batch processing. However, for doing batch processing, you need to consume a significant amount of memory, which is not always practical, and thus there is a place for and there is a need for a streaming-friendly algorithm for threshold learning. And in order to present this streaming-friendly algorithm, I will take you to a completely different problem and completely different world of a dog food tastiness challenge. We want to know which of the two brands, Pedigree and Theo, is good, is tasty, is favorable by dogs and dog owners. We ran sort of a poll, and Theo got 12 likes out of the 20, and Pedigree got 6 likes. However, we want to do threshold learning here, so we set threshold of at least 3 cities and at least 3 breeds, meaning that we accept that something is tasty only if we've seen testimonies, we've seen indications from people from 3 cities with 3 breeds of dogs, and here only pedigree passes. And the reason for that is that you can see that, for example, in the red part of the table, you can see that San Bernard owners and none of them said that Theo is good, and people from San Francisco also never said that Theo is good. But for pedigree, we have a pretty balanced voting spread between the different cities and the different breeds. And one of the reasons for that is that we had, you can see many voters that have Pomeranians and many voters from New York, and all the 6 people that are New Yorkers with Pomeranians, all of them liked Theo, but we didn't want to count them all as new ones, but we want to count them somehow together, and this is exactly what we wanted to achieve. So how to implement this? So we think of pedigree as an object, and of the tastiness as a fact, a Boolean fact. It can be tasty or not tasty. And the threshold learning is focused on 2 attributes, city and breed. Each of them has threshold of 3. And for each one of them, we keep a set of all the cities we've seen so far. At the beginning, we've seen no data, so we know nothing. So everything is turned off. For Theo, we have the same, and we can have another fact, whether the dog food is nutritious or not. Data comes in, and now we feed the data into the system, and we see that now the sets for cities and breeds for pedigree tastiness are, we have a set of 3, and thus we passed the 2 tests, and we're good. We believe that pedigree is tasty. However, for Theo, we have only 2 cities, and we have only 2 breeds, and it didn't pass any of the tests, and therefore Theo is not accepted as tasty. So looking at that, so what we did, actually, we learned the Boolean fact that an object X has a property Y. Looking at that from a memory consumption perspective, then the memory consumption is proportional to the number of objects, the number of properties, facts, the number of attributes, and the threshold. However, it is independent of the size of the data, which is exactly what we wanted to achieve. How to use Boolean facts for Web API profile? Well, it is pretty straightforward. During the training, then for every request we see, then we extract for every fact that is interesting for us, we can extract a flag fact X seen. And then we'll take all these fact X seen flags, and we'll collect them together, see which thresholds are passed, and then we'll get into the profile fact X allowed, in case we passed fact X passed all the tests, and if not, we'll have fact X prohibited. During the inference, we have a profile, and now for every new request, we can extract all the fact X seen from this request, and if we have a fact X seen that is also prohibited, then we have a violation, and this is what we wanted to achieve in the first place. So we can learn Boolean facts, and we can use them very effectively for the web profile. And the next question is, what can you do with Boolean facts? It seems like a pretty limited model. And in the next couple of slides, I hope to convince you that this model is not limited at all, actually, that it can obtain quite a lot. So let's start with what I call objects or containers. We want to learn what are the hosts, the methods, and the query string parameters and the relations to host and methods. So actually, this part is pretty much straightforward because all the things that we want to learn actually have a Boolean nature. URL X at host Y, this is one Boolean fact, allowed. Cookie X at URL Y, allowed. Query string X at URL Y with method Z, allowed. All of them are Boolean facts, and again, this is pretty easy. It works very well, no problem here. However, what about the parameter traffic profile? We have data types, we have ranges, character set, regular expressions. Can we all also deal with these guys? So I will dive into the area of parameter type. So suppose we have a parameter and we want to classify, to include in the profile the type of this parameter. Now we will have a num is a numeric type allowed flag, and which we'll try to learn. And if we will not learn it, then we will have a different flag in the profile, numeric type prohibited. We will also have a non-numeric type allowed and non-numeric type prohibited. In the next slide, I will show how exactly these are used. They are very important. We have the same for string, for Boolean, and also for none, which represent a situation where we don't have a value for this parameter, which is also, of course, an important thing to learn. So suppose that we want to include in the profile that the type is a string, and then we learn the flag str type allowed, okay? But we are not learning the flag num type allowed because we didn't see num type, or maybe we've seen num type, but we didn't see it in a way that passes all the threshold tests. We also we didn't see non-str type too much, so we don't allow non-strs within the profile, only strings. Now, if we see x equals abc or x equals x@gmail.com, then these are strings, we're good. If we see x equals 23, then actually we have num type seen, and it contradicts the num type prohibited, and there we go, violation. Another example, this time using regular expression, we want to enforce the fact that type is a mail address. The more I hope that you understand now that the more important is the prohibited part and not the learned part. And we learned that non-mail regex is prohibited. And the reason is that we didn't see many indications of non-mail values in the traffic for this parameter. And therefore it is not allowed, and therefore it is prohibited. And now, whenever we see x@gmail.com, then this is okay, because the non-mail regex scene is not there. However, if we see ABC, then the non-mail regex scene is there, and it contradicts the non-mail regex prohibited, and again, we have a violation. When it comes to mandatory parameters or optional parameters, then missing prohibited and missing allowed are the flags, the facts that we are using, and it is essentially very similar to what we've seen with the strings. When a parameter we want to represent the fact that it shall have no value or that it has multiplicity, then again we play with a non-none type and multi-occurrences facts. When we want to talk about a character set, then a non-B64 character set fact. When we want to play with particular special characters, and we say that ASCII 21 is allowed or prohibited, ASCII 7E is allowed or prohibited, etc. And when we want to deal with ranges, then here we need a little trick to do discretization of all of these ranges. Then we will not know exactly that the parameter is between 34 and 345, but it will have to, we'll split the domain into ranges. For example, we have greater than 5,000, greater than 500, lower than 10, and we can play with these facts in order to represent these ranges in a way that makes sense for the web security domain and attacks. So let me summarize. Data poisoning is a significant threat on learning mechanisms, especially when they rely on data from outside, with or without labeling outside. And it is applicable whenever this threat is there, whenever you are doing something meaningful and that someone cares about, which I hope for you that this is always the case for you. Threshold-based learning may provide an adequate, robust learning solution. The Boolean facts framework provides a streaming-friendly implementation for threshold-based learning of a profile. And although the Boolean fact framework at the beginning looks restricted, in fact, many features can be expressed through this framework. Thank you very much. And now we have time for a couple of questions.